you may remember that when we define the moments for univariate random variables. So, let us discuss that. Let x be a discrete random variable with the probability mass function, suppose Px of xi. So, here I belongs to 1 to like this 1 2. So, some range of x1, x2, x3 like this. Now, for the kth order moment is defined as, you can remember that we discussed it is mu m mu k dash expected values of x to the power k. This is nothing but for, because it is a discrete random variable, summation of x k to the power. So, here kth order moment. So, let us xi to the power k px of xi over sum is over xi. So, this is the kth order moment. If it exists, the sum exists, then this is the nothing but mu k dash. Now, similarly, for bivariate random variable cases also it will be defined like, let xy be a bivariate random variable, bivariate discrete random variable, with the probability mass function Px of xi yj, where I is 1 2 like this and j also 1 2 some values. It may be finite or it may be countably infinite. The k nth order, because here bivariate, so we have to consider two integer k nth order moment of xy is defined as so here the notation is kn, mkn. For knth, k are positive integer, mkn, this is nothing but, because it is discrete random variable, summation of I xi, sum over all the value it can take xi, sum over all the value yj it can take, then xi to the power k, yj to the power n pxy of xi yj. So, this is just a, you can see that the extension or to the bivariate random variable cases. Now, for this case, these are some special notation we have already discussed. It may be mu x for x random variable y. So, now for this is the okay. So, for k is equal to 1. So, let us consider some of the values. So, suppose here k is equal to, so we have to write for k is equal to 1 2 like this and n is equal to 1 2 like this. So, we can consider 0 also. So, if it is 0, then let us consider 0 also, 0 1 2 like this, and n is equal to 0 1 2. So, if k and n both are 0, so this become 1, xi to the power 0 is 1, yj to the power 0 is 1 for any values of xi and yj. This is nothing but the summation of this probability mass function. By the properties, this will be equal to 1. So, note that k is equal to 0, n is equal to 0, m 0 0 is nothing but 1. So, this is nothing but summation of xi yj pxy of xi yj, because it is a joint probability mass function. By the properties of the joint probability mass function, this should be equal to 1. Now, if you consider k is equal to 1 and n is equal to 0, so this is m 1 0. So, what is that? This is nothing but summation of yj, summation of xi. So, we will put this formula n is equal to 0. So, yj to the power 0, this become 1, only xi, and k is equal to 1. So, then this is nothing but xi pxy of xi yj. Now, if you do if by the assumption that the summation exists and we can interchange the summation. So, then suppose let us first take the sum of y j p x y of x I y j, then this become by definition this becomes the marginal probability mass function. This is nothing but x I p x of x I. So, by definition you know that the marginal probability mass function how we will find. If you take the sum of the other variable for a particular fixing the x I for any values of x I, you can find that if you take the sum of the other variable y j, then p x of x I. Then if you take the sum of x I p x of x I, so then this become, so what by definition you can remember that just now we wrote it. So, if you take k is equal to 1 here, it is expected of x nothing but x I summation of x I p x of x I, this is nothing but the mu 1 dash. So, this is mu 1 dash. So, this is nothing but mu x. So, that is why k is equal to 1, m 1 0 is nothing but mu x. Similarly, you can show that m 0 1. So, whenever you are taking k is equal to 0, n is equal to 1, that means m 0 1, this is nothing but mu y. So, similarly you can find it. So, we can do it also. So, here just whatever we discussed now, it is defined the k nth moment of a bivariate random k nth moment of a bivariate random variable x y is defined by m k n expected values of x to the power k y to the power n summation of x I y j x I to the power k y j to the power n p x y x I y j. So, whenever it is a discrete random variable. So, m 1 0 is nothing but a mu x and m 0 1 nothing but mu y. So, that is already we have discussed. So, now, so these things already we have discussed. So, now what will be the case when suppose k is equal to 2, n is equal to 0. So, then this is nothing but m 2 0. So, m 2 0 is by definition. So, this is x I, this is y j. Now, what is m k mth moment? So, m k n is nothing but summation of x I y j. So, n equal to 0, k is equal to 2, y j to the power 0 is 1. So, this is nothing but x I square p x y of x I y j. So, here also we assume that this summation exists and we can interchange this summation. So, this is x I square summation of y j p x y x I y j. Now, this sum, this is nothing but the marginal probability mass function of x. So, this is nothing but x I of x I square p x of x I. So, this is nothing but mu 2 dash in our definition. So, m 2 0 is nothing but mu 2 dash. So, hence we can find the variance of x is nothing but mu 2 dash minus mu 1 dash whole square. In this notation, this is m 2 0 minus m 1 0 whole square. So, this is the variance of x. Similarly, you can find the so actually this mu 2 dash with respect to the variable x only we take this notation, mu 1 dash also same. So, mu 2 dash we can write actually expected values of x square if we write some notation like for x. So, suppose this is x mu 1 dash x. So, then it will be variance of y will be similarly mu 2 dash for y minus mu 1 dash for y whole square. This is nothing but m 0 2 minus m 0 1 whole square. So, this is the mean and variances we can find here using this formula. So, now what about 1 1 m 1 1? So, whenever k is equal to 1, n is equal to 1, we will get m 1 1. So, this is by definition, this is summation over x I y j, x I to the power 1, y j to the power 1, p x y of x I y j. So, we may not have any simplified form here like because it is particularly for bivariate cases only. For invariate cases this measure does not exist, but this measure actually giving some kind of measure of association between x I and y j, like how x and y are changing with respect to their values. So, we will discuss this after some times, because now we will discuss the similar concept for continuous random variable. So, now we can remember that let x be a continuous random variable continuous random variable with the probability density function f(x). The suppose kth order moment, we already discussed in details that it is called the raw moments, central moments, moments around a point we already discussed, but here only raw moment we are considering, we are just saying that for simplicity kth order moment for x is defined as we denoted like mu x or mu 1 dash. So, let us because there are other variable x also, that is why you can write in first bracket x mu 1 dash x. So, this is nothing but which is equal to 1 minute. So, this is we discussed this is mu r dash, not mu x is the first order moment only, for here only kth order moment we are talking. So, mu k dash x is equal to summation, it will be discrete random variable, it will be continuous random variable minus infinity to plus infinity x to the power r f(x)(x) dx. So, similarly, for bivariate continuous random variable it will be extended. So, let xy be a bivariate continuous random variable with the probability density function f(x)y or xy. The knth order moment, moment of xy is defined as expected values. So, it is denoted as mkn, which is equal to expected values of x to the power k, y to the power n. So, this is defined as minus infinity to plus infinity, x to the power k, y to the power n f(x)y of xy. This is equal to minus infinity to plus infinity, x to the power k, y to the power n f(x)y of xy dx dy. So, this is the knth order moment. So, similarly, suppose k is equal to here for k is equal to 0, 1, 2 like this, n is equal to 0, 1, 2 like this. So, for k is equal to 0, n is equal to 0, we get m 0 0. So, here in this case also minus infinity to plus infinity. So, this is x to the power 0, y to the power 0, 1 1, and so this is f(x)y of xy dx dy. By properties of the joint density function, this should be equal to 1. Now, k is equal to 1, n is equal to 0, we get m 1 0. So, this is minus infinity to plus infinity, k is equal to 0. So, then x to the power k is equal to 1 x and y to the power 0 n. So, this is y to the power 0 is equal to 1. So, this is x and y to the power 0 1 f(x)y xy dx dy. Now, assuming that this integration absolutely summable and it exists, and then it is exist. So, we can change the order of the integration. So, then we will minus infinity to plus infinity x, this is minus infinity to plus infinity f(x)y xy dy dx. So, now what is this? So, you can remember that when we discussed that how to find the marginal probability density function from the joint probability density function. So, this is the joint probability density function. If you do integration of the variable y, then you will get the marginal probability density function. This is f(x)(x) dx. So, now if you compare with this univariate cases, this is suppose k is equal to 1, then you get mu 1 dash for the variable x. This is minus infinity to plus infinity x f(x)(x) dx. So, this is same as this value. So, this is nothing but our mu 1 dash x, or we simply notation is mu x, we denoted by this. So, similarly, m 1 0 is mu 1 dash. So, what will be k is equal to 0, n is equal to 1, we will get mu m 0 1. Similarly, you can find it is nothing but, so minus mu to plus infinitive, minus mu to plus infinitive. In that case, x to the power 0 1, y to the power 1 1 y. So, then f x y x y dx dy. So, then you can see that if you take first with respect to x integration minus mu to plus infinitive y minus mu to. So, let us write down in the next line. So, for the case k is equal to 0, k is equal to 0, n is equal to 1, we get m 0 1, this is minus mu to plus infinitive, x to the power 0 1, y to the power 0, y to the power 1 y. So, f x y of x y dx dy. Now, minus mu to plus infinitive y, this is minus mu to plus infinitive f x y, then dx dy. This term is nothing but you are doing the integration of the variable with respect to x, sorry, this bracket will be here. So, you are first doing the integration with respect to x, so you will get f y y. So, this is nothing but minus mu to plus infinitive y f y y dy. So, this formula is same as, similarly, this is nothing but mu 1 dash for the random variable y, or simply notation mu y. Now, if you take k is equal to 2, n is equal to 0. So, let us write next page. Suppose for k is equal to 2, n is equal to 1. So, what we will get? K is equal, sorry, n equal to 0. So, this is nothing but m 2 0. So, m 2 0 is x to the power 2 x square y to the power 0 1 f x y x y dx dy. This is minus mu to plus infinitive this. So, now we will assume that we can change the order of integration, all the conditions satisfied for that. So, then x square minus mu to plus infinitive f x y first is dy and then dx. Now, this is nothing but the marginal probability density function x square, and then this is nothing but f x x dx. So, this is nothing but mu 2 dash for the random variable x. Similarly, you can find that similarly if you take k is equal to 0, n is equal to 2, we get m 0 2, just same. Similarly, you can find this can be nothing but mu 2 dash for the random variable y. Hence, the variance of x you can find, variance of x is nothing but mu 1 dash x minus mu 2 dash x minus mu 1 dash x whole square. So, it is nothing but m 2 0 minus m 1 0 whole square. Similarly, variance of y, it is nothing but mu 2 dash for y minus mu 1 dash for y whole square. This is nothing but m 0 2 minus m 0 1 whole square. So, these are the some of the values. It is very similar to the discrete cases, this values it is coming. So, this is represented in this expression also. This is the definition, all computation again it is shown here also. So, x y for discrete random variable mu x mu y we are getting, for similarly x equal x square y square also we are getting, and similarly for continuous cases also it is given here, mu x and mu y are represented in this way, and similarly x equal x square y square also. Now, we will discuss what will happen for k equal to 1 and n equal to 1. So, k equal to 1 and n equal to 1. So, for suppose for k is equal to 1 and n is equal to 1, for discrete case we have already written, discrete case we have already written. So, m 1 1 for continuous cases minus infinity to plus infinity, minus infinity to plus infinity, this is nothing but 1 x y f x y x y dx dy. So, there is no any other we have to find out. For a particular example we can find this value also. So, if this exists, so now this we cannot relate with univariate cases, because this measure is not it does not exist for univariate. It is for the bivariate cases also this measure is different case, but this measure actually it has some significance, we will discuss. So, whenever we will discuss how we can relate two random variables, suppose x and 2 y are two random variables, we have some measure of association, how they are associated each other. So, one of the measure is it called covariance. So, how we will define this covariance? So, covariance, let x y be a bivariate random variable, it may be discrete or continuous, be a bivariate random variable, be a bivariate random variable, so this is the definition covariance. The covariance of x y denoted by cov x y or sigma x y is defined by this relation, the covariance of x and y, covariance of x and y or between x and y is denoted as COV x y or denoted as or we can denote like sigma x y. This is covariance between x and y, sigma x y, is denoted by x y or sigma x y, defined by covariance between x and y is expected values of x minus mu x is the mean of the x into y minus mu y. So, if you subtract their mean and then you take the moments of their first order moment actually after subtracting, this is nothing but the covariance between x and y. Now, it has some simplified form like variance, we found the simplified form, here also we can find some simplified form. So, it can be simplified like suppose this expected values of x minus mu x, y minus mu y can be written as x y minus mu x into y minus mu x into y minus x into mu y plus mu x mu y. Now, because expected value is a linear transformation, so it can be so we know that the properties of the expected value, this is nothing but expected values of x y minus expected values of mu x into y minus expected values of x into mu y plus expected values of mu x into mu y. Now, mu x mu y are constant. So, these are some real number after taking the expected value, these are some constant. So, then again we will apply the this properties of the expected value, this is expected value of x y minus this is mu x into expected values of y minus, because by the properties mu x is a constant. So, some constant into random variable is constant into expected values of that random variable minus again here similar, it is a constant into expected values of x plus, because it is a constant mu x and mu y are constant. So, it is expected values of a constant is constant mu x into mu y. Now, if you simplify these things, we will find this is equal to expected values of x y minus see that mu x into expected values of y is nothing but mu y. So, this is mu x and expected values of y mu y minus mu y into expected values of x, it is but the notation is mu x. So, this is mu y into mu x plus mu x into mu y. So, that we find mu y. So, then this one of the mu x and mu y it is cancelled. So, finally, what do you get? Expected value of x y minus mu x into mu y. So, then in our notations it will be coming like the expected value of x y is nothing but m11. So, what we found the moments. So, in this moment we computed, here you can see that. So, or you can, so m is k is equal to 1 and n is equal to 1 both the cases. So, whenever we compute it, So, from the definition, somewhere we represented it. In this definition you can see that this is suppose the definition. So, if you put k is equal to 1, n is equal to 1, this is nothing but expected values of x y, because m k n is defined by expected values of x to the power k into y to the power n. So, finally, what finally m 1 1 minus this is mu x is nothing but m 1 0 and mu y is nothing but 0 1. So, this is the covariance between x and y. Now, covariance provide a association between the two random variable x and y, but it is not unitless. So, it depends upon this value depends upon the what unit we are considering. So, if you change the units, that is why we need, so it is not bounded. So, it may have different values. So, any values it can take. So, now if you want to compare different random variables, suppose there are x and y two random variables and another random variables z and w, and we know the covariance between x and y and covariance between z and w, and we want to suppose compare that how x and y are related and by the covariance and z and w are related, because they depends on different units of measure. So, we cannot compare. That is why to make it unitless, so some different measure introduced, it is called the correlation coefficient. So, the correlation coefficient is defined by the correlation coefficient is defined by, so this is nothing but this correlation coefficient, it is denoted by rho x y and is defined by rho x y, either rho x y or we denote by rho x comma y first bracket. These are the notation we follow, and this is nothing but this definition it is given covariance of x y, this is covariance of x y by sigma x sigma y. So, what is sigma x sigma y? Where, so we can write in this way also, covariance of x y by root over of variance of x into variance of y. So, this is sigma x y by sigma x sigma y, where, so sigma x y already we denoted covariance of x y, and sigma square x is nothing but variance of x, and sigma square y is equal to variance of y. Next, we will discuss some properties of the covariances and with respect to how they are associated, and also the properties of the correlation coefficient. By the values of the correlation coefficient, how we can say how x and y are related, that we can say how they are related by the values of the correlation coefficient, and some of the properties of the correlation coefficient next we will discuss.